Okay, let's go back to this slide again. Okay, after what we have discussed earlier, okay, when we talk about the noise, because the noise is a random signal, then we cannot simply minus between our G and our noise in order for us to obtain our ideal F there, ideal image F there. So that's why we cannot, because the noise itself is not deterministic signal. Okay, if the noise is deterministic signal, for sure that you can replace that one with certain formula, okay, certain expression. But because since this noise is not a deterministic signal, it's a random signal, so you cannot just simply minus between your degraded image G with your noise in order for you to obtain your F. Okay, and before we go deep detail on how actually we want to model our noise, then I would like to remind that what we have discussed here. Okay, if you go back to this whiteboard, we still in this condition number one. Okay, phase one or condition one, where we assume there's no degradation function or blur, the cause of degradation due to the blur. Okay, we assume that our image is only affected with noise. So what we have discussed in this slide is actually we still at this stage where we want to model our noise, because we assume that our image G is only affected with this noise. Now we are trying to model this noise. However, one of the problem is that our noise is not deterministic signal, so that's why you cannot simply to obtain our F, because why we need to obtain our objective, we want to obtain our F, because again our F head over here. Okay, if we can achieve 100% similar to our F, that is the ideal, or our goals there, because we want to make sure our F head is very close, or in other words, if we can get the exactly F, then that is should be excellent. So now the problem is, in order for you to obtain F from these cases, it's not just simply you take the G and minus the noise, because the noise is not a deterministic signal, it's a random signal. So that's why you cannot just simply just subtract between G and F, G and noise to obtain your F. Okay, so that's why right now we try, since this is a random signal, noise is random signal, that's why we try to model our noise. Okay, since it's a random signal, we try to represent or try to model our random signal or our noise with to represent it in term of to represent it using the PDF, because PDF is one way to represent the random noise. Okay, so that's why now at this stage of try to model the noise using, or try to model the noise using PDF, because PDF is the only way to model the noise. Okay, and then we also give you some expose on one example of PDF is Gaussian distribution function or Gaussian function. Okay, so now let's go back to this slide. Okay, so how to model the PDF of our noise. Okay, that's the proper word to use. How to model the PDF of our noise. Okay, again that is also I have explained earlier. Okay, how actually we want to model our noise. Okay, the first step is actually, if okay, let's say you want to because this is we just assume that we want to investigate our digital camera. Let's say you have a digital camera, and then you for sure that the image that you obtain from the digital camera is you cannot get 100% image from the camera which is free from degradation factor. Okay, and then now in our case, that assume that the image that we obtain by using our digital camera is affected with noise. Okay, and it's free from degradation function. Okay, this is the first case, and we right now we are discussing about the phase number one, or the condition number one, where assume that, for example, your camera only produce the image which is affected with noise only. So one way how to model the noise is that you take any small patch. Okay, small patch means that a small patch of image that consists of homogeneity pixels. Okay, in this case, you can also, one way to do that is, you can um okay, for example, this one. Okay, you just take your camera, and you capture any homogeneity surface, like for example your plain wall, and then once you capture by your digital camera, and then you obtain the histogram. So what are the reason of doing this is because, okay, this is example of the image that you capture, the image that you capture by using your digital camera. Remember that, again, why we want to model the noise, because that is the noise that produced by your camera. Okay, the problem is with the hardware, it's not with the image. Okay, is the image is affected with noise is because the noise is come from the camera. So that's why now we are investigating what are actually the degradation factor that occur in your hardware. So that's why we are now try to model that. Okay, but in this case we just assume that your camera is free from any cause of degradation, image degradation. Okay, but the only one that affected your image is the noise, or the additive noise. So how to model the noise that affected your image is, just simply, okay, it's just simply the first step, you just capture some image. I just assume the suitable image that you can capture is your plain wall, because your plain wall don't have so many color, you have a homogeneity colors there, is very plain. So you just capture by using your camera. Then once you obtain the image, okay, this is example of the image. You can see this is the example of image of your wall. Okay, or in other word, in this slide they are using the gray board. Okay, some gray board of image you capture by using your camera, and then you plot the histogram. Okay, that is the first step if you want to investigate what type of noise affected your image. Okay, for this mechanism, I will like to discuss through this thing that I have drawn in my whiteboard here. And then again, like I said, if you talk about the noise, in the noise is random signals, then one way to model the random signal is you can model it by using, or represent it by using the PDF model, because PDF model is the only thing that you can model your noise or represent your noise, because your noise is in random signals. So again, and then now the issue is how to model the PDF of noise. Okay, so again, one way you need to do is you need to capture a plane surface like this one. Okay, and in this case they call it a gray board. Why they use a gray board? That is because if you imagine that, if you are using the gray board, because the gray board we can say the color is something at the middle, it's not close to 0, it's not too close to 255. If you are using close to 0 and 255, it's very hard for you to investigate, because that's why we are using a gray board, or a plane which is the color is not so dark and not so bright. Okay, because later when we want to plot the histogram is close at the center. Okay, it's close to 1 to 8. Okay, that is if in practicals. Okay, if you talk about the image with 8-bit per pixels. So now let's discuss the simplest mechanism. Okay, the same things, I will discuss the same thing, but I'm using the example here I'm using is not 8-bit per pixels. Okay, in term of, if you talk about the intensity level resolution. Okay, this is the same gray board, but now it's not 8-bit per pixel, it's only 3-bit per pixels. Okay, so assume this is our gray board, because it's more easy for me to discuss in this whiteboard, because now we can also as well, you know, give you some example in terms of how to do it in hand calculation. Okay, then you know the step. So once you okay, then the other reason that why why we want, okay, when we want to investigate or to model the PDF of noise, we always capture the homogeneity surface. Okay, that is because the reason behind it is because if your image or your camera don't provide or don't produce the noise that affected your image, then the gray board should look like this. Okay, because you are capturing some homogeneity surface, and then for sure that the intensity value inside the image for each and every value should be same. Okay, and then if you plot the histogram of this image, then for sure that you will get something like this. Okay, okay, if you want to plot the histogram of this one, okay, this is my intensity for this slide. Okay, for this chapter we are using Z there to represent our intensity value. Okay, so this one is similar with R in the previous chapter. Okay, in point processing we use R, so this one we are using Z just to tally with the slide in this chapter. Okay, if you plot the histogram, okay, the ideal gray board should look like this. Okay, where the point is only here is a 4, then the total pixel here is 6 times 6, should be 36 pixels. Then this is the histogram look like, meaning if your image is free from noise, then you will produce the single bar in your histogram. But that is impossible to be happen. Okay, when you capture the image, and because of the imperfection in your digital camera, when you capture this homogeneity surface, then your image is affected with some noise, which is, of course, we cannot get something like this. Then you obtain something like this. Then how to model the noise? Through the PDF. Okay, the first step, okay, this is the first step. The first step you need to do is you need to plot the histogram. Okay, the concept is similar with the previous chapter when we discussed about histogram equalization. You upload the histogram, image histogram. What is, okay, image histogram? You need to plot. Okay, I just give example here. Okay, if you generate the histogram, it's look like this, and this is the frequency of each and intensity value occur here. Okay, because the highest is 4, which is 18 pixels, and then from here you convert into normalized histogram, because when we talk about the normalized histogram, that is your PDF. Okay, you convert into your PDF. Okay, this is your PDF. Okay, the shape is same, the difference is just the amplitude there, or the vertical value, because now vertical value must divide by the total number of pixels, which is 36. So later when you do hand calculation, you need to simplify this one. This one should be 1/2, this one should be 1/9, and so on. Okay, but this is actually now normalized histogram, or in other words, this is the PDF. Okay, so since you see this PDF, okay, from here you can see that our PDF right now is a bell shape. Okay, it look like a bell shape. So if your histogram shape, if your PDF shape is like a bell shape, then you can conclude that our image is affected with Gaussian noise. Okay, that is how we interpret. Now we already identify my image is affected with Gaussian noise, because my PDF shape is a bell shape, and when we talk about the bell shape, is actually a Gaussian function. So that's why we conclude that our image is affected with Gaussian noise. Okay, and of course it's not just finished here. Okay, you need to investigate more. if you talk about the Gaussian noise, okay, Gaussian noise, there's a two parameter you need to obtain. Okay, if you refer to this slide, okay, it's a same concept here. You have a gray board image like this, you plot the histogram, seeing it's a bell shape like this one. This also a bell shape, it's a bell shape. Then you conclude that your image is affected with what we call as a Gaussian noise. And then if the image is affected with Gaussian noise, if you talk about the Gaussian noise, there's are two parameter that you need to obtain, which is the mean of your Gaussian noise and the variance of your Gaussian noise. Okay, if you remember about the Gaussian function, there's a two parameter, which is the means and the variance. Okay, so if you talk about Gaussian, then you need to measure two parameter, which is mean and the variance of, and this will become the parameter of your Gaussian noise that affected your image. Okay, so how to measure the mean and variance? Okay, then you can refer to this slide. If you talk about the Gaussian noise, then this is the formula on how to formulate your mean and variance. Okay, I just copy this formula and put it here. Okay, this one and this one. Okay, so as you can see, actually there's a two way to measure to calculate your mean and variance. Okay, one is you can use the formula in the slide, which is this one and this one, and you can also use a typical statistical formula. Okay, this one I think you already you already familiar with these two formula in order for you to measure the mean and variance, because this one is a statistical, you learn it in statistical class. Okay, meaning, okay, doesn't matter whether you use this one or this one, you should get the similar mean. Okay, the difference is that these two formula, okay, if you talk about this formula, you are simply, calculate the mean directly from this image. Okay, because this formula, okay, it can be interpreted that you are directly calculate the mean here, meaning that if you want to calculate by using this formula, what you use is that is equal to your mean is equal to, you have a 544, so you just take the number 5, that is Z1, that is Z1, and then, okay, because you have Z, the n here is a 36, because you have a 36 number of pixel, then this one Z1, Z2, Z3, Z4 up until Z36. So you just plus together 5 plus 5 plus 4, and then you plus together until 3, and then you divide with 36. So that is how you use this formula, okay, to get the means. However, this formula, which is in the slide, actually you are getting the same mean, but you are utilizing the PDF, okay, for this formula. Okay, if you see, if I want to use this formula, okay, what is the first Zi here? Okay, the S here is this one. This all here is S. Okay, that's why they put here Zi is a subset of S. Okay, meaning that everything here is under S. So I don't want to focus more on the how to interpret the formula here. I just want to give you some how to give you some understanding on how to interpret, simply interpret this expression is actually Zi. Okay, the first Zi is 5. Okay, you have here the Zi number 1 is 5, so it should be 5 over here. And then what are the probability of 5? If you refer to this PDF, 5 is 6 over 36. So you must 6 over 36. Sorry, let me undo back this one. Okay, the first Zi is 5. So what are the probability 5 occur in this? Okay, if you talk about the probability of 5 occur is this one. So this is the pz, p when z equal to 5. So then that is actually your 6 over 36, and then you plus the next one is what, 4. Okay, how about 4? Then 4, what is the probability of 4 occur, which is 18 over 36. So 18 over 36. So you will do this one until okay, you only you need to do this in 5 4. Okay, you must do this actually I write this one is in a proper way. You should write in this way. Let me make it here. So it should be 0, then you have the probability, plus 1 probability of 1, plus 2, what is the probability of 2? Okay, meaning that this one is 0, this one is 0, and 2 is 3 over 36. Okay, if you refer to this one, okay, 3 over 36, and then you plus 3, which is 6 over 36, and you do this until 7 0, and then you will realize that when you get the mean here, the mean value here is similar with this one when you calculate using this formula. Okay, it's the same things. Okay, don't get confused with that. Okay, and then that is how you calculate the variance. And then after you calculate the variance, you need to calculate the that how you calculate the means. And then after you calculate the means, then you need to calculate the variance. And the variance also you can do the same things, meaning that you can use this formula, where this formula is based on the PDF. And if you want to directly calculate from the matrix, you can also do, which is by using this formula. Okay, you will get the same things. Okay, once you get these two parameter, then you can, what you already identify that the image affected your the noise, the noise that affected your image is Gaussian noise, and then you know that is a Gaussian noise. So what you do is that, and the Gaussian function is it can be expressed in this way. This is the Gaussian function. Then you can you can write here, and you can conclude more detail. Okay, my image, okay, the image that the noise that affected my the noise that affected my image is a Gaussian noise. Okay, and that Gaussian noise can be model, the noise model can be represented by this formula, which is our Gaussian formula. Okay, which is in the slide there. Okay, and then of course once you measure the mean and variance, then you can replace it. Okay, this one is mean. Okay, this one is mean. Okay, let just use this slide, is more better. So you can say that so from here we can conclude that the noise affected my image is a Gaussian noise, and that Gaussian noise can be modeled, and can model by this expression, the PDF of my noise. And once you already calculate the mean and variance, you can replace that value inside this formula. Okay, that's how you represent the noise affected your image, or that's how you model the noise that affected your image. Okay, it's a true PDF, and then that PDF should have some formula. Now in this example, because our PDF is in bell shape, we conclude that is Gaussian noise. And if we talk about the Gaussian function, this is the Gaussian function. Then in this case, our noise have what is the mean of our noise, and what is the variance of our noise. Then you replace that mean and variance in this formula. Okay, so that's how you do.